To answer this question, you should really review Millikan's experiment and how that worked to really get into being able to answer what is happening here. However, we're going to go ahead and start off by drawing a diagram. So we have two parallel plates. This top plate, as defined in the question, is negative, and the bottom plate will be positive. There is an oil droplet suspended between the two plates. And of course, it's acting where there's some E or FE for the electric field pushing upwards and FG pulling it downwards. We know that the sum of all the forces has to be equal to 0. And this helps us determine the sign on the droplet. So the sign on the droplet is going to be such that it is able to be repelled by the bottom plate because that's where it's being pulled down from. So the charge on the oil droplet must be positive so that it is being repelled upwards. So this oil droplet here is positively charged, so that way it's repelled upwards, working against gravity. To determine the magnitude, we're going to create the expression where we have the force of the electric field equal to the force of gravity. So this then goes ahead to give us Q epsilon is equal to mg. We're going to sub epsilon in for what we have, or some of the information we have from the question. So delta V over R is equal to mg. We can now rearrange, simplify this, and isolate for Q, which is equal to mgr over delta V. And if we go ahead and sub in all the information we know, so the mass is going to be 1.0 times 10 to the negative 13 kilograms. Gravity is always 9.8, and we'll say newtons per kilogram. And the radius, the distance between the two is 5 centimeters or 0.050 meters, and then the potential is 120 volts. By solving for that, we're left with 4.1 times 10 to the negative 16 coulombs. That's the magnitude of the charge of the drop. Finally, we're asked to determine whether or not the droplet has an excess or a deficit of electrons, and then of course by what amount. So before doing any calculations, we can figure out that it is going to have a deficit of electrons, given that it is positively charged, based on the way we've set up Millikan's experiment here. So we can then go ahead and take our equation, which we've rearranged, n equals q over e. We have our value for q, 4.1 times 10 to the negative 16 coulombs, and our value for E, 1.602 times 10 to the negative 19 coulombs. This leaves us with 2.54 times 10 to the 3. Because it has to be positively charged, this is a deficit of electrons. So the number of electrons in deficit is approximately 2,500.